Hi students, in this lecture I am going to discuss previous year's IIT questions. Let us see first one. Let's see the passage given. A uniform thin cylindrical disc of mass m and radius r is attached to two identical massless springs of spring constant k which are fixed to the wall as shown in the figure. This is now cylindrical disc connecting two springs to the axis of the disk. Okay, the springs are attached to the axle of the disk symmetrically on either side at a distance d from its center. The axles are massless and both the springs and the axle are in horizontal plane. The unstretched length of each spring is L. The disk is initially at its equilibrium position with its center of mass at a distance L from the wall. The disk rolls without slipping with velocity v bar equal to v naught I cap. The coefficient of friction is mu. Right, first focus here the key points. So it is given that unstretched length of each spring is L. Disk is initially at its equilibrium position with its center of mass at a distance L from the wall. That means when it is in equilibrium, springs are in its natural state. Okay, the meaning of spring length L, and this is now distance given L from the wall. Disk rolls without slipping, velocity given V naught I cap. See diagram carefully. So velocity given along positive x-axis. And at this instant, disk is in equilibrium position. Okay, means it is just like mean position. See here what happens. Because of this velocity, disk rolls in positive x direction. Then springs will elongate. Okay, so this is just like mean position. It is moving now towards the right extreme. That means while moving towards right extreme, net force will be left side towards mean position. Okay, let us see. First of all, see what we have to calculate. The net external force acting on the disk when its center of mass is displaced x with respect to its equilibrium position is. We have to find net external force. Let us see. First of all, displacement is x from equilibrium position. Suppose now this is a disk. Okay. Velocity given now, right side. Then see spring force. Spring force will be, it is 2kx. Because of both the springs, it is 2kx. And you can see from equilibrium position, it is now rolling like this, moving towards right side. So rolling is like this, means velocity right side. Okay, suppose frictional force at this contact. Let us take it as right side. We are not knowing here direction of friction. Assume it is now right side. Frictional force. Since it is now rolling without slipping, it will be static. Okay. Now see what we can write. Since it is now rolling without slipping, Write the force equation for center of mass. Then, so we are taking that net force is left side. Okay. So I'm writing here net force 2kx minus f. This is net force, which is equal to mass into acceleration of center of mass. Okay. So we have taken ACM is left side. That means what we are saying is, since velocity is given, speed keep on decreases. Speed keep on decreasing means acceleration must be opposite to velocity. Okay. It is left side. Next. Now focus torque equation. Torque equation about center of mass. Then torque is only because of frictional force. So F into R, that is equal to I into alpha. I value mr square by 2 in the place of alpha. See, ACM is equal to R into alpha. So in the place of alpha, it is ACM upon R. Okay. Now see calculation part. R cancel R square and R. And we want to calculate net force. Net force means mass into acceleration of center of mass. That means we can eliminate now F. So in the place of F, M ACM by 2. Right here, M ACM by 2. Take that one to right side. 2kx is equal to 1 plus 1 by 2. 3 by 2 M ACM. Okay. That means from that net force, F net force equal to mass into acceleration. That is now how much? 4kx upon 3. That is net force acting on the disk. Okay. Right. Now let us see the next question. The center of mass of the disk undergoes simple harmonic motion with angular frequency equal to. You can see here displacement is right side, but net force is left side. Okay. So we can write in vector form net force is equal to minus 4k by 3 into x. Okay. Or if you want acceleration equal to minus 4k by 3m into x. So this is of the form minus omega square into x. Right? That means omega value, it is root of 4k upon 3m. Okay. That is omega value. Next, the maximum value of V naught for which the disk will roll without slipping. So maximum value of V naught. Now see what we can say here. Velocity maximum. So when velocity maximum, this will come to rest temporarily. When this comes to rest temporarily, elongation will be maximum, right? Or we can do one thing here. Frictional force, which is static. I am writing. Suppose this is equation 2. From equation 2, frictional force equal to M ACM by 2. We got M ACM value how much? M ACM value 4kx by 3. Half of that 2kx by 3. That is frictional force, which is static. Now this frictional force should not cross limiting value. Okay. This frictional force should not cross limiting value. Here k is a constant. That means we have to focus now. When X becomes maximum, frictional force becomes maximum. I am repeating. When X becomes maximum, frictional force becomes maximum. And that maximum value should not cross limiting value. So maximum value can be limiting value. Okay. So now what we are doing is calculate maximum value of X. So for that we are using now energy equation. Let us energy equation of velocity given V naught at equilibrium position. So having only kinetic energy of m V naught square into 1 plus beta. So 1 plus 1 by 2. That is 3 by 2. Right? That is equal to. Now see what we can write here. When it comes to rest temporarily, it is purely in the form of potential. Right? That means we have right now spring potential energy. Now see what is spring potential energy? It is equal to half k x square. X is here maximum. Okay. Into 2 because 2 springs. Cross check once. I have written here kinetic energy equal to half m v naught square into 1 plus 1 by 2. That is equal to when this comes to rest temporarily, this kinetic energy completely converting into it is spring potential energy half k x square maximum. Now see what we get. 2 and 2 gets cancelled. X maximum. X maximum is equal to what is left here. M V naught 3 by 4. 3 by 4. M 3 by 4 M. Here K is left by K. This will come under root V naught square. It is V naught. That is maximum value of X. Now substitute that here. Frictional force maximum value mu mg. That is equal to 2k by 3 into X maximum value 3 by 4 m by k into V naught. Okay. So from this we are going to get the maximum value of V naught. Okay. That is V naught equal to, see how much we get. It is mu g into remaining, see what else left. Mu g into 3m by k. Okay, cross check once calculation. So we have taken energy equation. From that we got X maximum value. When X is maximum, frictional force is maximum. And that maximum value is now limiting value. Right? And remain just calculation part. Right? Let us see next one. Let's see the question given. The torque on a body about a given point is found to be equal to A bar cross L bar, where A bar is a constant vector and L bar is the angular momentum of the body about that point. From this, it follows that. So asked for 2 marks in 1998. Given torque on a body, A bar cross L bar. Okay. So now we have to focus the options. Let us see how to verify these options. So it is now given torque. So torque equal to A bar cross L bar. And L bar is angular momentum about same point. A bar is a condition given. A bar is a constant vector. Okay. Means direction and modulus values both are not changed. Right. See first option. dl bar by dt is perpendicular to L bar at all instants of time. So we are knowing that net torque is equal to dl bar by dt. Okay. Since it is now cross product, this torque is always normal to A bar as well as L bar, or you can say normal to the plane containing A bar and L bar. So option A, dl bar by dt is perpendicular to L bar at all instants of time. That is a correct one. Okay. Next. So next I'm focusing option C. The magnitude of L bar does not change with time. Now see carefully. dl bar by dt. Okay. It is always normal to L bar. Always normal to L bar means it changes only direction of L bar. If you remember, while learning a uniform circular motion, you just compare with that. Velocity is always along tangent velocity vector. Since it is uniform circular motion, acceleration is always normal to A bar. So A bar means rate of change of velocity. It is always normal to V bar. So here we have seen that modulus of V bar is a constant. It is changing only direction. Exactly same logic here also. dl bar by dt always normal to L bar. Therefore, it changes only direction but not magnitude. That means option C. Magnitude of L bar does not change with the time. It is a correct one. Option C. Next, option D. L bar does not change with the time. That is wrong. Because just now we have told that direction of L bar changing. Okay. That means option A is correct. Option C also correct. Now focus option B. The component of L bar in the direction of A bar does not change with the time. So here only possibility. This is a possible if A bar and L bar are mutually perpendicular. Okay. Then what happens? Component of L bar along A bar, it is L cos 90. That is 0. So now we have to focus how to verify that. Okay. So here one thing we have to say, tau bar normal to L bar always. Tau bar always normal to A bar. Okay. But L bar direction keep on changing. Therefore, direction of tau bar also keep on changes in such a way that it is always normal to L bar. Okay. At the same time, it must be always normal to the plane containing A bar and L bar. So here what I am saying is, for example, A bar is along x-axis. L bar is along y-axis. Then tau bar is along z-axis. Now fix A bar. Okay. Now L bar is changing. That means rotate L bar means rotate y-axis and z-axis. So z-axis is now, it is tau bar and y-axis is now L bar. Okay. If you rotate now y-axis and z-axis, you can see this tau bar always normal to yz plane and this tau bar always normal to L bar, right? That means we can say that this L bar is normal to A bar. So this is the only possibility which satisfies this condition. That means we can say option B also correct. Okay. Let us see next problem. A thin uniform bar lies on a frictionless horizontal surface and is free to move in any way on the surface. Its mass is 0.16 kg and length is root 3 meter. Two particles, each of mass 0.08 kg, are moving on the same surface and towards the bar in a direction perpendicular to the bar, one with a velocity of 10 meter per second and the other with 6 meter per second as shown. The first particle strikes the bar at points A and other point B. Points A and B are at a distance of 0.5 meter from the center of the bar. Diagram you can see here, 10 meter per second at A, 6 meter per second at B. The particles strike the bar at the same instant of time and stick to the bar on collision. Calculate the loss of kinetic energy of the system in the above collision process. So asked for 8 marks in 1989. Let us see. Given mass of the bar and its length, particles both have same mass. Next, points A and B at a distance of 0.5 from center of the bar. See meaning of this. From center of the bar, A and B at same distance. These 2 points having same masses. That means center of mass of the bar and these two particles system is again center of the bar. Okay. Both have same masses at same distance from center. That's why center of mass for these two particles and bar is again center of the bar. That means it rotates about center of the bar. Okay, let us see. First, make the given diagram. This is uniform bar. Now 2 points A and B. 2 points A and B equal distance. Their velocities. One is 10 meter per second. The other one, it is 6 meter per second. Mass given 0.08 kg. Distance from center, it is given distance from center 0.5 meter. Center, let us take it as C center. Then AC equal to base. That is equal to 0.5 meter. Okay, now let us write here momentum equation because net force equal to 0. Writing momentum equation 0.08 into 10, same mass into 6. That means 10 plus 6, 16. 16 into 0.08. That is equal to, now total mass. Total mass is 0.08 into 0.08 plus mass of the bar 0.16 into VCM. Okay. Then VCM is equal to VCM equal to, see calculation, it comes out to be 4 meter per second. So first we have taken a law of conservation of moment. Now consider conservation of angular momentum because we want to calculate loss in kinetic energy. Then see what we have tried. Initial kinetic energy minus final value. Initial value means directly we can write a half into mass 0.08 into 10 square. Next, again half into 0.08 into 6 square initial value minus. Now here system is having translatory motion. At the same time, it rotates about center of mass. Okay, that means we have to consider half into total mass into VCM square plus half I omega square, half I omega square. That means we require omega value. Already we got VCM, right? So to find omega, so now we are taking conservation of angular momentum. Rotation is about common center of mass. So it is now writing LCAM. Then see what we can write. We can write 10 into it is M B R. R is now 0.5. See, because of this about point C, it is a clockwise. About C for this anti-clockwise. Okay. I am taking clockwise positive minus M V R 0.5. That is equal to I into omega. So when you are taking I value, we have to calculate now I value for both the particles. Okay. And for the rod. For the rod, it is L square, ml square by 12 per particles. 0.08 ml square, 0.5 whole square into 2 because same mass, same distance. That is now I1 into omega. Now simplify this. Then we are going to get omega value 2 radian per second. Okay. And we got omega value and we got VCM. Substitute both values, VCM and omega here. Already we got I value here. Okay. Substitute that. Then the value comes out to be loss in kinetic energy. That comes out to be 2.72 joule. Okay. So it is just a matter of writing momentum equation to find VCM, then writing conservation of angular momentum to find omega value. Okay. Let us see next one. A uniform circular disk has radius r and mass. A particle also of the same mass m is fixed at a point A on the edge of the disk as shown. The disk can rotate freely about a horizontal chord PQ, that is, at a distance r by 4 from the center C of the disk. The line AC is perpendicular to PQ. Initially, the disk is held vertical with point A at its highest position. It is then allowed to fall so that it starts rotation about PQ. Find the linear speed of the particle as it reaches its lowest position. So asked for 8 marks in 1998. Let us see. Right, first make a diagram. It is a disk. Disk. Center of mass here. And axis of rotation. Axis of rotation at a distance r by 4 from center. When this point here reaches bottommost point, that means see what happens. So now I'm making diagram. Axis of rotation rotates means. So now how we have to draw the diagram. It will be now like this. Center of mass at a distance r by 4 below. Okay. Initially it was above, now it is below. And you can see the point A. Now this will be point A. Okay. So to find velocity of A, we have to find omega because it is not pure rotation. All points except the points on the axis of rotation, remaining all points will follow circular path. So velocity of A or speed of A is equal to its distance from axis of rotation r by 4 plus r 5r by 4 into omega. So now we have to focus how to get omega value. So here there is a loss in gravitational potential energy which converts into rotational kinetic energy. See what is that loss? This a particle will come down. Initially it was r plus r by 4, 5r by 4 above this axis. Now it is a 5r by 4 below. It has come down by 5r by 2. So loss in gravitational potential energy mg into 5r by 2. Next center of mass r by 4 above. Now it is r by 4 below. So it has come down by a distance r by 2. This is a loss. 5 by 2 plus 1 by 2, 6 by 2 means 3. 3 mgr. This is loss. And this loss converts into rotational kinetic energy, half 5 omega square. And psi value how much? Above this axis. This is now parallel to diameter of the disk. Okay. For a disk, above diameter value is mr square by 4. Above this axis. So we have to use now parallel axis theorem. So m into square of r by 4. This is for disk. For particle, m into distance equal to 5r by 4. Okay. And this value comes out to be, see how much? It is 15 by 8. Right? So 15 by 8 mr square. Now see calculation part. 3 mgr is equal to half I value 15 by 8 mr square omega square. Right? So 3 here 5 times. So m r gets cancelled. Omega equal to what? That's like 16 g upon 5r. Okay. 16 g upon 5r under root. This is omega value. Now take velocity of A. That is equal to 5r by 4 into root of 16g by 5r. 16. So now see cancellation. 4 and 6 gets cancelled. and you can take this one inside 25 r square, that becomes 5 that is now velocity of field. So it is just taking here conservation of mechanical energy, and next it is simply r into omega. R means distance from axis of rotation, that is now 5r by 4. Okay, so I hope you got a clarity.